To wrap up a couple things from last class. At the very end of last class, we talked about what happens if someone asks you to differentiate ln root, I think this was the same example I gave, ln root x triple 3 over x to the 5th times sine cubed x, yeah? And we talked about how that looked really hard, and actually you had a bunch of homework problems on this, how that looked really hard, but in fact wasn't that hard, because if you write this as y equals ln root x squared plus 3 over x to the 5th minus sine cubed, then you can use a bunch of log rules to break this up into little pieces, yeah? Okay. And so, all right, what happens is you apply all these log rules, and okay, I can just kind of do this in my head because I've done this before. It's going to be ln of the top minus the ln of the bottom, but then that's also to the 1/2, so you get 1/2 ln x squared plus 3 minus 5 ln x minus 3 ln sine x. And so this logarithm is really just great because it splits quotients up into differences, it splits products up into sums, and it splits powers up into products. And now we have a very easy thing to differentiate. Cool? Okay, so that's a thing. But, and this I didn't get to say, I was really rushing at the end of last class to try to do this, and I think it was a bad idea to try to rush. Suppose we have a different problem. Take this problem. Y equals sine 4th x times x cubed over tan to the 5th x times the 4th root of x cubed plus x. Okay, well this is equally terrible as before. And my goal is I want to differentiate this, right? So I want to know what dy dx is. Well, I don't know how I am going to do this. This seems like it will be really hard. And that's because just looking at it, I have to do the quotient rule. But inside the quotient rule in the numerator, I have to do the product rule. And inside the product rule, I have a chain rule. And in the bottom, I have a product rule and a chain rule inside of that and another chain rule inside of that. So this is like terrible, right? But now, there is no logarithm here to like save us, right? Okay. What can we do? Booyah.
Add one.
Add one. Booyah says, just because there's no logarithm already built into the problem, I know logarithmic differentiation. And so I shall use logarithms to do the exact same thing that happened over here. Follow? So what we do is, we take the natural log of both sides, and then we use the properties of the natural logarithm to break things up into tiny little pieces, and then we differentiate. So do this right now in however many steps you need. Take the logarithm of this and break it all down into as many small pieces as you can. Alright, do you get
Whoa, that's fast.
ln sine x plus 3 ln x minus 1/4? Did you get that?
No.
Let me double check if I possibly made a mistake. No, I don't think I did. I think that's right.
I just did some cancellations beforehand.
Which cancellation?
You can take out a sine x on the top and bottom, sine to the fourth x on the
Oh.
top and bottom.
Yeah, that's true. Never mind that though. If you don't do that, then did you get this? Someone back me up? I feel like that's right.
Yeah, that's right.
Okay. Good. I just kind of showed off by doing it all in one step because I've done this so many times before. But it actually gets pretty easy after a while because it's just like break it up, break it up, break it up, break it up, and just kind of apply all log rules. All right. So now I have this very, very simple thing. Now what do?
Differentiate it.
Just differentiate. Yeah, this is the new thing that we learned in the last 20 minutes of class, which is now what I'm going to do is I'm going to take the derivative of both sides. So this is what's called implicit differentiation, is the actual name for this. Specifically, this is called logarithmic differentiation. Logarithmic differentiation, which is kind of an application of implicit differentiation. Okay, so I take the derivative of this whole thing, and okay, that part I think you guys know how to do. I think you know how to do all of it, but what is the derivative of ln(y)? This is what we did last class. I think most people got it, but maybe some people were still a little bit confused. I'm asking for the derivative of ln(y) with respect to x. So I'm changing x a tiny, tiny little bit, and I'm trying to figure out what happens to ln(y). All right, well, this is like a chain rule situation, right? Because the rate of change of ln of y depends on the rate of change of y with respect to x and the rate of change of ln with respect to y. So the derivative of ln of something is 1 over the something back inside for the derivative of the something. This problem is kind of annoying. I think I could have made a simpler problem, but oops. So anyway, we can still do this though. Now differentiating the right hand side is just going to be like for the derivative of ln of sine, the derivative of ln of something is 1 over the something back inside for the derivative of the something. Here, this is just going to be 3 over x. Here, this is going to be minus 5. The derivative of ln of something is 1 over the something back inside for the derivative of the something, so that's secant squared. Minus, and then this will be 1/4 times, well again the derivative of ln of something is 1 over the something back inside for the derivative of the something, so that would be 3x squared plus 1. Who is with me? Are you guys like roughly as fast as I am, or like 30% slower or something like that ish at this? Just kind of like know all the rules. Woo! Okay, so then the final answer is, what is the derivative of this thing?
Sine to the fourth x times x cubed over 10.
Yeah. So then the derivative of this is going to be y times all that stuff. But y is like the original thing again, right? And so the final answer to this problem, believe it or not, is like sine fourth x times x cubed over 10 to the fifth x times the fourth root of x cubed plus x, but then times like all this crap. So like whatever this is, 4 cotan plus 3 over x minus, I don't know if that simplifies, I'm too lazy to simplify that, so I'll just leave it, minus 1 over 4 x cubed plus x, and then the top is actually 3x squared plus 1. So that entire giant mess is actually just the derivative. Okay, so that's called logarithmic differentiation. And I want to stress that this is a case in which logarithmic differentiation was optional. We could have, but it would have taken way, way, way longer from a computational perspective. We could have differentiated just using the product rule, quotient rule, chain rule. Okay. But then there are other cases in which logarithmic differentiation is not optional. This is like logarithmic required. And this is the thing we did at the very, very end of class, where we said, let y be like x to the x. Are you moving the camera? Let y be x to the x. And I also would like to just like to say that I think I tried to do this problem with like 2 minutes left before the bell rang. This y equals x to the x thing, this is not an exponential function. It is also not a power function. And perhaps this is worth mentioning. Can you spin the camera a little bit? I have like a warning of some things that you're not supposed to do. because there are these things called power functions. And what is a power function?
It's good.
It's a function of the form x to the n, where x is changing, but n is a constant, as we know. Okay, and we have seen what the rule for differentiating a power function is. It's just like nx to the n minus 1. Okay, then you have these other functions called exponential functions. And they are not power functions. They are, in fact, just like different things. Okay, but if you're really, and we know that the derivative of like 2 to the x, for example, we proved last class that the derivative of this is like ln 2 times 2 to the x. Okay, so now I would like to warn you that if you are very sleepy and not paying attention, and perhaps you're having a bad day or you're thinking about something else, then the most horrific thing imaginable will happen. And it's so bad that I can't write it on the board because that would be like mean to the board. So I have to write it on this sideboard, and then we'll perform a ritual cleansing. Okay, the thing that's so bad that I hope it never happens to you or any of your loved ones is if you go to try to differentiate 2 to the x, and you're like, that's just a number to the number, let me just do like, you know, x times 2 to the x minus 1. No! Very bad. That is very bad and very wrong and just total garbage. This is not true. This is an exponential function. This is a power function. They're superficially similar in that they both look like this, but here it's the base that's changing. Here's x. Okay, good? Okay, good. All right, so we're just going to put this on. So don't be that person. So we're just going to put that on the ground. Can you step up and then jump up and down on that 3 times? Okay. Okay, that whiteboard has been literally cleansed. Okay, so back over here, this is yet another totally different function. This is not a power function, and it's also not an exponential function. It's something else. Both the base and the exponent are changing. One reason why we've never talked about this function before in all of pre-calculus is because without calculus, you basically can't do anything with this function. It's not even clear what it's doing, 0 to the 0, who knows what that is, like it's very strange. Okay, so, let's just redo this conversation we had at the very end of class. What is the derivative of, how can we find the derivative of this function?
L on both sides.
Yeah, now we are going to again use logarithmic differentiation, but this time we have to use logarithmic differentiation. So we have to rescue that princess because it's way up, stuck up there. So we go ln, we take the ln of both sides, and now we use our exponent of log rules to bring that down, and now we differentiate both sides with respect to x. Booyah.
Can't you just raise both sides to the e, or like to e up at both sides, and then use the chain rule? Okay, wait. Yeah, I will explain. Booyah is right. First, let's do this. So does everyone see what I'm doing? By taking the log of both sides, I now have brought things down to where I can deal with them. And now we take the derivative of both sides with respect to x, and the derivative of ln y must be the derivative of x ln x. And well, what do you get? What is the derivative of ln y? 1 over y, back inside dy dx.
dy dx. And what do we get over here?
Ln
Derivative of
x
the first times the second plus the first times the derivative of the second. And so, in fact, what we end up with is that the derivative of this function is y, which is x to the x, times ln x plus 1. Who is with me? Okay, good. Booyah made a comment, which is there some other way to do it that doesn't involve this long process? Yeah, there is. If you're very big brain and you prefer this, you can just say that if I want to take the derivative of x to the x, then I think what he wants to do is rewrite it as e to the ln of x to the x. Most people find this to be more confusing, but if you somehow like this better, then so be it. Why is this a good idea? Well, first of all, it's true that these are the same thing, and then you can apply the chain rule in a more straightforward manner by saying the derivative of this is going to be, well, it's going to be, what is the derivative of e to the something? Oh no, I guess first I want to bring down the x, right? Yeah. So now I want to apply the log rule, but like inside the e. So that's x ln x. That's the whole point of taking the log in the first place. Okay, so now, so that's still just the function. Now I take the derivative. What's the derivative of e to the something?
E to the something.
E to the something back inside for the derivative of the something. And so now I differentiate x ln x, which is just
ln x plus 1.
ln x plus 1. And then I just reconvert this back into e to the ln of x to the x. Yeah, I'm just doing the same problem in a different way. Who followed? Now I just reapplied the log rule, and now I just reapply the fact that that's just x to the x. Okay, so I don't know. To me, that seems just overly fancy. So that's why no one teaches it this way. But if you look at these two approaches, they are of course the exact same thing, logically speaking. Over here, I just decided to temporarily call it y first, so I didn't have to think to do this kind of thing. But if you like this better for whatever reason, then so be it. All right, yo.
Are we gonna need are we gonna ever have to analyze a problem and say, okay, I know that we need to use the log differential?
You kind of have to do this anyway, I guess, and we'll see that in a minute. Okay, wait, so should we do one more of these, or is this just kind of like, do we have the point? When I say do one more of these, I mean, what is the general category of function that we've essentially just learned how to differentiate? Weird functions, specifically like function to the function. If I now give you anything of the form, like x squared plus x to the sine x, for example, you now know how to differentiate this, right? Mm-hmm. This is just a harder version of what we just did. Everyone, you want to do this for 1 second? Go. Do that problem. Take the line both sides. Apply log rule. Differentiate both sides with respect to x. We good?
Yes.
Yeah.
Derivative of ln y is 1 over y back inside dy dx. And here we just do it like normal. So that's going to be cosine times, this problem sucks too. First, just second. Oh yeah.
How do you resolve problems with continuity? Because the function's continuous on all intervals, I'm pretty sure. But the derivative between certain values, like ln, like x squared plus x is negative, and you can't take the natural log of that. So the derivative is non-continuous.
Yeah, advanced question. Not going to worry about it. Good question. That's what I say to Haley every 5 minutes. Good question, Haley. Advanced question. Not talking about it right now. Alright, good. Alright, who gets it? This deserves like 5 minutes of our time. We've given it 10. Let's move on. This is not the most important thing in the world. What is important is the general idea of logarithmic differentiation. One more small thing we can do with this. I promised you 2 weeks ago, when we first proved the power rule, I promised you that like, hey, the power rule like works for non-integer exponents. Just trust me, I said at the time. But I also said earlier, like 45 minutes ago, that you should never trust adults because they don't have things under control. So, you're probably thinking, damn, Mr. Rose, when are you going to prove the power rule for a rational exponent? Well, now is the time. Are you ready?
Yeah.
Woo! What is the rule for the derivative of x to the p over q? Or what have you been led to believe is the rule?
P over q x to the p over q minus 1.
Yeah, we've been just treating this as like, yo, I can just apply the power rule, which is like bring that down, and then it's x to the p over q minus 1, right? Okay, so I'll just throw a question mark in there. Is that really true, or am I living a lie? Oh, it is true. Watch this. Let y equal x to the p over q. Who has an idea of how to proceed from here? Just take the natural log of both sides, yeah. If you take the natural log, anytime you got something up high and you don't want it there, that's what log does, right? It just takes it down. So if you take the natural log of both sides, you guys following this? Then you rescue the princess, and then I now have a simple differentiation problem, which I'm doing implicitly. So the derivative of ln y, 1 over y, back inside, dy dx. And what's the derivative of p over q times ln x?
P over q times 1 over x.
Oh, this is p over q times, that's just a number, times the derivative of x is just 1 over x. Who's with me? I think you all are, mostly. Okay, so then, what is the derivative? Well, it's going to be y times p over q times 1 over x. But of course, y is just x to the p over q. So I have x to the p over q times p over q times 1 over x. And of course, that is exactly the answer that we were expecting, right? The coefficient is p over q. And now it's, I'm dividing by x, so now that exponent's like 1 less than it was. So this becomes x to the p over q minus 1. Woo! Okay, good. That was a thing. More things. I think this is like in the other room, my notes on this. Probably don't need notes.
Oh, Ryan, the original function isn't the original function isn't continuous with the negative 1 because it's a negative value to power, and that doesn't really make sense. It's like negative 1 to the end. That's not.
Okay. Something else. 2 more things we're gonna do today. We're gonna try to do.
Yeah, it only works. Like negative 1 to the end.
Alright, whatever.
Yeah, it's like all
There's like it's a continuous but
Okay, good. Alright, so all of this skill, hopefully we are now comfortable with this skill of implicit differentiation. What I'm now going to do is, what I'm now going to do is expand slightly the category of things we differentiate. And I'm just going to forget about functions. And actually, we've been kind of forgetting about functions for a while now, or I've been trying to get you to kind of like think about how differentiation is really about change, or rate of change between quantities, not necessarily functions. So what if I give you something which is just definitely not a function? What is x squared plus y squared equals 25 in fact?
Circle.
Yeah, it's like a circle. It's just some relationship between 2 variables. Never mind all that silly function stuff. I just got 2 variables. They're related in a certain way. How are they related? Well, they're related such that the sum of their squares is always 25. And as you all said, that's just a circle with radius 5.
Dude, I thought that was a lot.
Okay, dude, I thought it was a circle and I was right. Okay, so, good. Okay, take a point on this circle. Like, I don't know, say 4, 3. Please confirm that the point 4, 3 is a point on this circle.
It is indeed.
Oh, it is? Question that you might want to know. What is the slope of the tangent line to this circle? At the point 4, 3. Whoa. This problem can be done, I claim, without any calculus, by just knowing some basic math facts.
Yeah, can't you just use like trig?
Yeah, well, I guess trig, I don't think trig, I don't think is relevant. Someone say something else.
Well, it's the perpendicular line to the radius to the point.
Yeah, like geometry and stuff.
The negative of the radius to the point.
Yeah, it's basically what you said, but like with a negative in there. Alright, whatever. Yeah, what does it mean? Sure, what does it mean if this point is 4, 3 anyway? It means that I go like over 4 and up 3, right? That's like the whole meaning of the ordered pair 4, 3. Well, if that's true, then this line, which is the radius, has a slope equal to 3/4, of course. Yeah? Okay, but then you just use a fact from geometry, which is that that these two are perpendicular, because every radius, every tangent line is perpendicular to the radius drawn to the point of tangency. And therefore, what do I know about the blue line? By like algebra 1 principles?
The negative reciprocal.
Yeah, it has slope which is negative 4/3. And so, alright, done. We solved the problem. Okay, but we could also take a calculus approach to this. In the calculus approach, you think of this line as being, well, a tangent line in the kind of a calculus sense. And what I really want to know, what I want to know the slope of that tangent line is, near 3, what is the ratio between the infinitely small change in x and the infinitely small change in y? That's just what the slope means, right? We already think that the slope is 4/3, but this slope is really delta y over delta x as we take the limit as delta x goes to 0. That's just what slope is, right? Change of y over change in x. Okay, so if I want to find the slope of this line, then what that really means is I want to just find dy dx. I would like to know what is the ratio between the infinitely small change in y and the infinitely small change in x for the tangent line to this curve. How can I do that? Well, I've just like, now that I know the chain rule, now that I'm comfortable with logarithmic differentiation, let's move beyond logarithmic differentiation to just full-on implicit differentiation. And I'm just going to take the relationship x squared plus y squared equals 25, which is just a relationship that the variables x and y have with each other. And I'm just going to differentiate both sides of this relationship with respect to x. So we're just going to take the derivative with respect to x of both sides of this equation. Are you prepared for this? Sure you are.
Yeah.
Okay, what do you get on the right-hand side?
0.
You definitely get 0. What do you get on the left-hand side?
2x.
I have to differentiate two things. They're being added, so we just differentiate them one at a time. What's the derivative of x squared?
2x.
2x. Okay, moment of truth. Booyah, don't shout it out. What is the derivative of y squared? 2 derivative. 2 derivative. Okay, if you're not paying attention, you might think that the derivative of y squared is just 2y. But that's not quite the whole story, because we are differentiating with respect to x. We are asking the question, what happens when x changes by a tiny bit? If we want to know, if we're asking what happens to y squared, specifically, when x changes by a little bit. And so this y squared is really a composite of two functions. There's the inner function, y, which is just something that depends on x. and then there's the outer function squared. So it's not, the derivative of y squared with respect to y would be 2y. But the derivative of y squared with respect to x is, chain rule says, the derivative of something squared, 2 something, back inside for the derivative of that something. And what is the derivative of y? Just dy dx, yeah. Who is with me? This is the same thing we've been doing for the past 2 classes on with logarithms, but there was nothing special about log, right? This is true for any function. Who is, are you guys all seeing what I'm seeing? Okay, maybe you are, maybe you aren't. All right, so now I have an equation, and I can just like solve this equation, right? 2y times dy dx equals negative 2x, and I just divide by 2y, and what do I get?
Negative x over y.
Negative x over y.
Can we like open a window or something? It's very hot.
Yeah, that's just gonna make, well, maybe not. Well, my papers are gonna blow away. Just like, don't wear a hoodie. Sorry.
Oh.
Yeah, it is very, very warm. Good thing we'll all be home in our temperature controlled, just wearing sandals and just like chilling.
Oh, Zane's.
Good. Wait, what have we just done here? We've just found the derivative, and wait, wait, oh my god, YouTube. Wow. Okay, oh yeah, okay, what is she explaining? Okay, good. Alright, what is this? This is a formula which will tell you, for any given ordered pair x comma y, what the slope of the tangent line to the curve is. So I just want to, this is sort of like a new thing now. Dy dx is negative x over y. So suppose I now say, alright, well what's dy dx at the point, well I don't know, take the point 4, 3 for example. Then all I do is I just plug in 4 and 3 into this formula. You should think of this thing in the box as a formula which takes as input the coordinates of a point on the curve and gives you back the slope of the tangent line to the curve. And, well, what do you get if you just plug 4, 3 into this equation?
Negative 4/3.
You get negative 4/3, which is precisely what we had above, yeah? And actually, you could do this in general if you wanted. You could confirm to yourself that this is the right formula, because if there is a point x comma y on this circle, then what that really means is that that's x and that's y. So what that really means is that the slope of that line is y over x. And so of course the slope of the tangent line to the curve would be negative x over y, which is exactly what we found using calculus. Okay, so here once again I've solved a problem with calculus that we could have solved without calculus, so maybe you're not that impressed. But this process, or this strategy, can be used to find all kinds of other tangent lines to other more complicated things. Okay, so